Accidental asymmetry in the dark sector. We consider confining gauge theory similar to the standard model quantum chromodynamics, which has quarks and antiquarks and gluons as fundamental particles above a critical temperature. Below a critical temperature, confinement happens. That means that all particles have to be color neutral. Those can be either baryons made of 3 quarks, or mesons made of a quark and antiquark, or glue balls made of gluons. And those two later states can decay to standard model particles because they're not protected by any symmetry. The baryons, however, are stable since they are protected by the dark sector baryon number, and those particles are the interesting dark matter candidates that we want to study. We look at the regime where the quark mass in the theory is much larger than the confinement scale. This is a very interesting regime because we know from lattice studies that the phase transition in this case happens as a first order phase transition. The quarks are just spectators and the gluons dominate the entire dynamics. Now, what happens in the first order phase transition is that the correct vacuum starts out as expanding bubbles, and those bubbles squeeze the quarks and antiquarks together in pockets of the wrong vacuum, and the only way for the quarks and antiquarks to enter the correct vacuum bubbles is to form color neutral states. That means baryons or mesons, or to just annihilate away to standard model particles. We have studied a set of local Boltzmann-like chain reactions that lead to the annihilation of the quarks or the formation of baryons and computed the symmetric survival factor. There's another way for the quarks to survive the phase transition, and that is by pure chance. In any of the forming pockets, there will be some amount of quarks or antiquarks that will have no partner to annihilate with. We can compute this amount by the law of large numbers by just taking the square root of the number of the particles that are in this pocket initially. So the asymmetric survival factor is found just by normalizing to the initial number of particles, and is given by 1 over the square root of n of the initial particles in each pocket. We find that this accidental asymmetric abundance is much larger than the symmetric survival factor. The number of particles in each pocket is set by the dark matter mass. So now we can find the correct dark matter mass that is needed to reproduce the correct radic abundance. In this plot, the correct abundance is given by this magenta line. Above that line we have too much dark matter, below we have too little. So the mass we find is between 1 and 100 peta-electron volts, which is way larger than what we expect from a thermal WIMP. That means that dark matter doesn't have to be that dark after all. By being so heavy, it just has a very low number density. So that makes us rethink the way we search for dark matter. Maybe we look for something that is actually just very rare and quite strongly interacting with our sector.